There are two models used for value added. One is the gain model, the MRM model, which looks at tests that are done consecutively, 3rd, 4th, 5th, 6th, 7th, and 8th grade English language arts and math, and the univariate response model, or the predictive model, which covers grades 5 and 8 in science and high school end of course tests, these non-consecutive tests. As we look at the two models, the report that goes with those, the gain model on the top uses an NCE calculation, that's the normal curved equivalent, which ranks the students in one year and lets us compare those students to the next year. And we look at values that show how much higher the average NCE was from a previous year, or lower in some cases, like this negative 2.6. The predictive model uses a predicted scaled score to determine the gain or the lack thereof. So as we look at the model, for example, 2 years ago, in this one we see a negative 0.9, so this group of students dropped from their predicted score. So as we look across, we see in this report the number of students. Well, which term are we looking at? In this top row, we're looking at a value from 2 years ago, and then 1 year ago, and then last year, and then the 3-year average. This allows us to evaluate the program over time. The number of students, the N size, the average score. So as we look at this, 2 years ago, this group averaged 708.9 scaled score. Their percentile rank, this is different than the NCE, and what they were predicted to have done. They were predicted to have been 709.6. They were less than that. This was their average predicted percentile. And we come up with the growth. Just like we come up with the growth up above, the calculations to get there are different. They use different values, but the end result looks very similar. And we have a standard error, and we have a standard error on our top report as well. So as you can see, that's the basics of it. Let's look at it a little bit more. So coming up with this predictions, and some people question that and how that's calculated. Let's look at this example of a hurricane off the coast of the United States. If this is all we know about this particular storm, we can't make a prediction. If suddenly we know nothing about hurricanes, we had never seen one before, and we see a satellite image that says, oh, there's a big storm off the coast. What can we say about that? Well, we need to know a little bit more about that particular storm and storms like that. So knowing where the storm was the day before or a few hours before, whatever the case may be, we can make a little bit more of a prediction because we can see this general path that this particular storm is taking. As we move on and get a little bit more historical data, we can get a little bit better projection of the path. And if you look at this closely, you can see that there's a cone in here that shows us the most likely path of the storm, and then an even wider view. Think of that like the standard error, that we know that in one standard error it'll go more likely down this middle, and 2 standard errors it would go down this wider path. But either way, we can be relatively sure that it's not going to go way off in some totally different direction, although those are still possibilities. So with even more information, we can even narrow that path down even more. So the more historical information we have about this storm or storms like this, the better off we are at making this prediction. So what the calculations look at is, where did storms that were just like the storm we just saw, where did they end up going? Based on wind patterns and where they had come from and so forth, we can develop this historical model of storms, and then we can find a storm in the future that has the same characteristics of the one we just saw. And that's essentially what they do with the data that they're looking at with the projections and the predictive model. Here we have a student named Sally, and Sally is in end of course geometry, and we know what Sally has done in this case in her math tests going backwards in time. We have several years. We even have an algebra test in here. So we have several data points, as well as we have her English language arts and any science tests that she had taken. We have a really nice historical picture of what Sally has done. So we're able to predict where Sally will be with some degree of accuracy. We know that she is about 61.6% likelihood of being proficient. And with these percentiles, projected percentiles and so forth, they can narrow that down to a predicted scale score. Well, when those tests are done, like I said, we'll have the average score and we'll have the predicted score. We know what the results will be once those tests are done. We know that value after it's done, so we just find the difference between where we predicted them to be and where they ended up. So looking at this in a little bit bigger view, we have a student named Whitney and a student named Ethan, and then the rest of the class, 6 students, actually 12 students, and we have all of their expected scores based on their history and divided by, and then averaged out. We have an average expected score of 651.4. Once they take the test in the spring, we take the actual score and calculate the average, and they had a 649.2 average score that the score that they actually achieved. So we're taking, in this case, the average score, the 651.4, minus what we expected them to get, 649.2, and they have a negative 2.2. Now the SAS Institute that does the calculations use many more decimal places and a few other little pieces, and sometimes even though we see the numbers and do the subtraction, it won't exactly match what we see on the report because of rounding issues and so forth. But we can take a look at this. Here's the row of data that we used. This was an English language arts test of the class with Ethan and Whitney. There were 469 students in the class. We expected, we didn't show that many in the previous slide. The average score that they achieved was 649.2. They had been predicted to get 651, and they scored 2.2 points lower than what they were predicted. That's their growth. There's a standard error which allows that 2.2 to be plus or minus 0.6, but their growth measure is negative 2.2. So, and to wrap this up, the predictive model differs in that it uses scaled scores instead of ranked NCEs, normal curved equivalents, like the GAIN model. Both of them give us an end result of the gains or losses of that group of students. And remember that these calculations then can be applied to subgroups such as the races, students with disabilities, English learners, disadvantaged students. They can be calculated by the class, by the school, by the district, and as opposed to the GAIN model where they're compared across the state, these are compared with how they were predicted to have done.